Good evening, everybody. I'm Seth McGowan, the president of the Adirondack Sky Center in Tupper Lake, New York. We're a not-for-profit organization, and just looking at the guest list tonight, I think many or most of you have been with us before, so you know something about who we are. But let me tell you more specifically about our organization and what we do. Our goal really is to make the universe accessible to everyone. I personally believe, and I think that all of our astronomers, amateur and professional, believe that the universe belongs to everyone. It's not just for those who are, you know, scientists. That everybody has the right, let alone the ability, to feel like they're part of their own universe. So it's all of ours, and we remind everybody that the wilderness doesn't end at the tree line. The original wilderness was above. In fact, everything that's in our wilderness came from above to begin with. So that's why we call it the wilderness above. We do free public observing programs as often as we possibly can, typically on Friday nights, depending on the season of the year, and then additional times when we can. Here's just one of the outdoor beginning presentations that we have. And then we move inside to the inside of the roll-off, where visitors have a chance to look at the objects through high-powered telescopes. This is actually a private party, a father, wife, and their son, just for his birthday. I think we're there just to look at some fun stuff. We also take our Starlab portable planetarium to schools in the area and give them a real immersive experience, looking up at the sky, teach them how the Earth moves and how that makes the sky appear as if it's moving, teach them about constellations, star birth, star death, all of those fun things. And then we do other STEM-related school visits, even do a little teaching of astrophotography, just having everybody understand their place in the universe. We do a number of after-school programs where we do everything from telescope making to experiments with light and planetary and collisions and so forth. So it's a lot of fun. It's a whole family experience. Some of our after-school programs, some of them are just for children alone. And of course, our growing in popularity Cygnus series of live virtual lectures that began technically as an outshoot of COVID. We had been doing years of in-person lectures, which we will get back to, but those were accessible to people who happen to be in the area. These virtual lectures has greatly expanded our audience and our reach in our effort to help everybody feel like part of their own universe. In our not so distant future, actually in our immediate future, we built an additional concrete stamped pad on our existing roll-off roof observatory. You can see that observatory there. People would normally just plant themselves on the grass to the south of that observatory. But with this concrete stamped pad, we have benches, we have lighting. It's a much more, I'll call it humane experience for people that come, and certainly much more enjoyable for us. So we're looking forward to using that. In fact, it was finished just as the first snowflake fell, and we really haven't had a chance to use it with guests and visitors yet. So we're looking forward to a thaw at some point and getting back outside and doing some presentations outside before we go in. We are in the middle of developing our plans for our planetarium. You may recall in the past that we had a full Astro Science Center that looked kind of like this. You can see that planetarium, that round dome in the middle right side, is where we are right now. So we've eliminated for the moment the rest of the building and are focusing only on the planetarium itself for now. So that's the roll-off roof observatory. That is the planetarium with a classroom and other features that will allow large groups to come in and be part of that experience. kind of a rough architectural diagram looks like this. Here's the planetarium on the left side with fixed seating. And right next door to it is our classroom with movable seating so we can use it for multiple purposes. And here's just a kind of a general idea of what that might look like. In Tupper Lake, we are in the what I refer to as the heart of darkness. That is where we're located, right there. And you can see how far away we are from these other major cities through Canada, Rochester, New York, up through Boston. We have visitors regularly coming to take part of our observing programs in Tupper Lake because we are the dark spot in the area. In fact, to the best of my knowledge, we're the only public observatory operating for visitors in the Adirondack Park itself. So we have quite a nice feature there for people who are coming to visit, and they do. If you haven't heard, there's an eclipse coming right through Tupper Lake, and we've managed to organize that so the sun will go behind the moon for a little while. And that will happen on April 8th in 2024. We're working with the community and the entire region, in fact, to plan some great events for that time. So if you're interested, we are in totality here. If you're in an area that's not, I would encourage you to come on up and be with us for that. We'll have some great things going on during that time. Well, getting back to why we're here tonight, we are getting back to our, wait a minute. Okay. See, it's Zoom that's doing it. It's the whole, it's got to be it. I don't think you can see my screen. There we go.
Can.
All right, thank goodness. Coming up in our lecture series, of course, tonight is Jeff Miller, who's one of our regulars and a favorite among our fans. Next month, again, the first Thursday of each month is when we do these. Next month, Eileen O'Donoghue, also from St. Lawrence University, will be here. On May 4th, Josh Thomas from Clarkson. And June 1st, Gib Brown from, you may know from WPTZ, will be with us here for our live lecture series. I want to mention that all four so far, these are all board members of the Adirondack Sky Center and Observatory. So we are just thrilled that that they're so active with us and so much a part of what we do. So thank you in advance, Jeff. That's the plug. Okay. Please wait. Oh. Yeah. Okay. Hang on.
All right. Well, I got mine up. How's that sound?
All right. Well, yeah, I'm going to just hand off. I don't know what's happening here. It's somebody's taking over. I'm going to stop sharing and welcome Jeff Miller, who's like I said, had done these before. He's at St. Lawrence University, teaches astronomy and physics at there for over 30 years and counting. He's I don't know, he's been a member of our board since 2004. He maintains without a peep, maintains our website, does these talks, offers his expertise and so forth to us on a regular basis. He lives in Potsdam with his wife Cheryl and his dog Willow. And when he's not teaching or grading papers, which I think is happening more and more, he likes to hike, snowshoe with Willow, cross-country skiing, photography, and watching old sci-fi movies like Armageddon, when they tried to deflect an asteroid heading towards Earth with the space shuttle. If only we had some more information about how that would work. But it turns out he might have that for us tonight. So with that, thanks for being with us, Jeff, and doing this, and take it away.
Thank you for that introduction, Seth. And yes, everything you said is 100% accurate. So tonight, I'm going to be talking about part of NASA's planetary defense strategy, because we know that there's a lot of stuff floating around in space. And sometimes the Earth does encounter some of these objects. And the question is, what can we do to try to protect ourselves if we have some warning that a relatively large object, an asteroid, or maybe a comet is heading for us? So we're going to see what NASA's first step into taking some precautions to protect us. But first, I'm going to start off with my impression of Chicken Little, that the sky is falling. The sky is falling, especially if you like to watch science fiction or read science fiction, especially in movies. In the last 60 years, I just have a sample here of some movies that all dealt with objects on a collision course with the Earth. And of course, front and center is Armageddon. Fantastic movie, lousy science. For a lot of these movies, the only way that we could protect ourselves was to try to send as many nuclear weapons as we can to try and blow up some large object that we know is on a collision course with us. Well, it turns out that's actually not a great plan. So we're going to see what ideas the scientists at NASA have come up with. So why should we worry? Well, we know that the Earth has been hit many times over the millennia by extremely large objects. Some of them have done excessive damage, such as with the dinosaurs. Nobody sees any dinosaurs. Oh, sure, we see some ancestors of dinosaurs wandering around, but the dinosaurs are no longer here. That's because millions of years ago, the Earth was struck by a relatively large asteroid. It created a plume of material that was blasted in the atmosphere that basically choked off the sunlight. And so it changed the temperature, it changed the food, it killed the vegetation, and a lot of the larger animals could not survive. So I like this cartoon that I found, these dinosaurs. This is kind of my idea about not only eating salad, but also grading. I can't believe I ate all that salad for nothing. If you ask my wife, she will tell you I wait till the last possible minute to start my grading because, you know, if some cataclysm is coming or our alien overlords are coming to take over us, I don't want the last thing that I have done to have been grading a stack of papers. So always waiting for the last minute. Now, the dinosaurs were taken out by an event that we have referred to as the Chicxulub Impactor event. And basically a large asteroid that we think was maybe about 6 miles wide, 10 kilometers if you're north of the border, hit the Earth about 66 million years ago. This is a painting of what the crater might have looked like sometime after that impact. About 100, 110 miles across, maybe 12 miles deep. And trying to find bits from that. I'm not sure if they've actually found material from the original asteroid, but there are hints in in this particular area in Mexico that, yeah, this is probably where a very large impactor hit and wiped out the dinosaurs. But that was 66 million years ago. Why should we worry about ancient history? Well, let's move forward in history a little bit, and let's go to just 50,000 years ago. On the geological scale of things, that was just a couple of hours ago. So in Arizona is the Barringer Meteor Crater. And a meteorite that was made out of nickel and iron, very, very dense. It was probably only about 160 feet across, but it did strike the Earth and it made a crater that's about 3/4 of a mile across and about 560 feet deep. And the reason that we know what kind of meteorite it was is because all through the site, we have found fragments, some small, and there are actually a few very large ones. Fortunately, this large fragment, which weighs nearly 400 pounds, is at the observatory at Wesleyan University, where I went to graduate school. And yes, the graduate and undergraduate students, we used to take our turn and try to lift the meteorite, at least to be able to, impress if nobody other than ourselves. And yeah, I got it off the table once. A millimeter is all it takes. And that was it. Never did it again. So There are many of these, and they are very heavy, very dense. And you can see the kind of damage that something 160 feet across could actually do if it strikes the planet. Let's move up to more modern times. Now we're in the 20th century. In 1908, we think it was an asteroid, but not a heavy iron one, but more of a stony one that would break up easier. It didn't actually strike the Earth, but we think it was what we call an airburst. It actually exploded in the atmosphere somewhere from 3 to 6 miles above the surface of the Earth. Did not make an impact crater, but it flattened an estimated 80 million trees over an area of over 800 square miles. It took years, because this was such an isolated area, it took years before people could actually even get to this area to take pictures. There are no known fatalities. There are some rumors that perhaps 3 people died, but it was very sparsely populated area of Siberia. But you can see the devastation of something that didn't even strike the Earth. Another airburst, even more recently, 10 years ago. I happened to look at the date of this, like, wow, I've been talking about this one, the Chelyabinsk meteor, which exploded also over Russia. Russia doesn't have very good luck with meteors exploding over them. But it was February of 2013, so just over a decade ago. An asteroid that was only about 66 feet. That's a quarter the size of a football field. We think it was about 18 to 20 miles above the surface of the Earth. Another airburst, fortunately, did not strike the surface of the Earth, but it released enough energy that it was equivalent to about 30 atomic bombs, at least the atomic bombs that were on Hiroshima. Nobody was killed from this, but thousands of people were injured from shattered glass. It made such a boom when it exploded that a lot of windows actually broke. And the fascinating thing about this one was, well, not only was it, huge and visible to a lot of people, but in Russia, they were one of the earlier countries to adopt dash cams. And if you've ever spent time on YouTube, you go down that rabbit hole of watching Russian dashboard camera videos of all these horrendous crashes. People started putting dashboard cameras in their cars just because the police were so corrupt. They wanted evidence of, no, I really wasn't, running that red light or whatever. But that also means that during this event 10 years ago, there's lots of video of the meteor passing over Russia. And it actually helped because scientists could tell where they were driving or where these cameras were situated, helped to plot the position, the track of that asteroid as it flew over. So I'm going to show you this video. There's no audio here, just somebody driving, and it's 20 after 9 in the morning. Remember though, this is February in far northern Russia, so it's still dark. You can't see very much, and this guy's just tooling along, driving there, stopped at a light, and then disappears in front of him. Now watch, right in front of him, you'll see shadows appear. Look at how bright. There's actually people crossing there. You couldn't see them before. What's even more fascinating is everybody is just wandering across the street. People are driving. I watched a lot of these 10 years ago. Nobody in their car was exclaiming, "Holy cow, look at that." They might have muttered something under their breath and then they went on their way. That should tell you what kind of life that they would experience. It's like, oh, well, I guess we're going to blow up today. Maybe I should have told my wife I loved her before I left this morning. Who knows? So that was 10 years ago. We have an object you may recall from my last talk, which was just over a year ago, asteroid Bennu. And we sent the OSIRIS-REx spacecraft to go investigate it. And we actually had a lander to land on the surface and collect a sample, which is being returned to Earth this year in September. So Seth, I think I know what my next talk is going to be sometime in the fall.
Sounds
Hopefully
good to me.
we'll find what kind of cool stuff we get from that. Now, the interesting thing about Bennu, why were we interested in this particular asteroid, is that in the year 2060, it's going to pass relatively close to us, about twice the distance of the Earth to the moon. Now, it might seem to us that the moon is very far away, but in the cosmic scale of things, the moon it's not even in our backyard, it's in our back pocket. It's extremely close. So twice the Earth-moon distance, that's only like 500,000 miles away. And it's going to pass even closer in 2135, where it'll be half as close as the Earth-moon distance. So we sent this OSIRIS-REx spacecraft to Bennu so that we could better understand not only its composition, but its orbit. The more we understand its orbit, the more we'll be able to understand, is it really going to come close to this, in the next, 30, 50, 100 years? That stuff's really important. So why are we interested in this one? Not only is it close, but it is enormous. So here's a scale image that was created by NASA of Bennu next to the Empire State Building. It's a lot bigger than the Empire State Building. So something that large with a weight estimated to be about 80 million tons, if it's going to be half the distance of the Earth to the moon, we got to make sure that it's not going to be any closer than that. We have to really be prepared for any sort of close event. And just for scale, I added a scale image of the Chelyabinsk meteor. That's the one that was flying over Russia to scale. You can see that that one was just peanut size compared to Bennu. Really important to study its orbit and its composition, and hopefully, if it becomes necessary, to figure out what can we do to sort of give us a bigger buffer. One last story. Everybody probably heard about this. This was big news in January. NASA system predicts small asteroid to pass close by Earth this week. This was the end of January. And the caption from this picture says that the asteroid, which its orbit is marked in with the red line there, will pass about 10 times closer to the Earth than the orbit of geosynchronous satellites. Earth has a lot of geosynchronous satellites which orbit high above the Earth, but they always stay above the same position in the Earth. 10 times closer than that. That's really close. According to the article, that this asteroid that came close was about the size of a large truck and was going to pass about 2,000 miles above the surface of our Earth. There was no risk of it hitting the Earth, as it says in the bottom paragraph here. Just because of its size, even if it had, it probably would have mostly burned up, okay? But this one, even though you think about a truck flying through space, you'd want to be worried about it, but it's nothing on the scale of like Bennu. So what are we to do? We need to understand these objects that are near the Earth. So there's this whole category of near Earth objects, NEOs for short. Now this is a YouTube video and I didn't have time to download it. It's just linked to YouTube and it plays beautifully if I'm not running in Zoom. So, and when I tested before, it might take a little bit of time to download. Hopefully it doesn't hesitate too much, but there's a 2-minute video from NASA that clearly gives some nice graphics explaining what these near Earth objects are. So let's watch that. NASA makes some really slick videos. So it's nice to know that they've got our back. They're watching out for us. So there was this particular video was part of that video that you just saw that shows, and it was created back in 2018, and it shows all the known asteroids. Now, keep in mind that the asteroid belt is between the orbit of Mars and Jupiter. So Earth's orbit is this white circle, this is Mars, and this is Jupiter. We could see that there are hundreds of thousands of objects that we know of, that we're keeping track of. But some of them are close enough to the Earth, within the Earth's orbit, because there are collisions between these asteroids. Even though there's a lot of space out there, despite what it looks like in this animation, occasionally there are collisions between these objects and they come into an orbit that's closer to Earth. Now, the latest info is from 2 days ago, right? The 28th, which was on my calendar, Tuesday, I believe. As of Tuesday, there were 31,374 near-Earth objects known. Several thousand of them are close enough or large enough that they could potentially be a hazard sometime in the future. So NASA has to have a plan to keep watch on all these and for something to do to keep us safe if they're coming. Excuse me. So what will we do if we find out that something is heading for us? What are our options? The two most obvious ones, well, the first one is let's blow it up, because that's what we do. If you watch old science fiction movies, the two things that they always seem to put on a rocket ship was, well, every astronaut was armed. Who knows what they were going to encounter, but they definitely were going to shoot it. And they frequently had missiles or bombs on their rocket ships. So why don't we just launch a whole bunch of nuclear weapons and blow something up? A paper was published in Icarus back in 2019. A bunch of scientists did some calculations to figure out, okay, if an asteroid 6 miles wide, that's the size of the asteroid that killed the dinosaurs. If something that big was coming from us, at us, and we tried to blow it up, it would take 10 million atomic bombs to blow it up. That's a lot. There aren't that many, thank God. There are not that many atomic weapons on the Earth. Aside from that, the big problem with let's say we could destroy something in space, it wouldn't completely vaporize. There would be a lot of chunks, and there's no guarantee that there would all be little tiny chunks that would burn up in our atmosphere. So despite what they shown in Armageddon, where they have Bruce Willis with his crew land, dig a big hole, drop a nuke in there and blow this thing up so that it splits and goes around the Earth, there would be huge fragments that would still be left that would still cause catastrophic damage. And especially if they're spread out over a larger area, you could have them peppering the entire planet. So blowing things up really isn't an option. Can we move it? How about if we can just push it, just shove it out of the way? Sounds implausible, but that's the most likely option. And these are the things that NASA is now working on. And so that is what led us to the DART mission. DART stands for Double Asteroid Redirection Test. They said, you know what, if we could have a collision of an object, a satellite, with an asteroid coming to us, perhaps without trying to blow it up, we're trying to deflect it. We want to change its orbit. If we have enough advanced warning that this asteroid is coming towards us, maybe we can change its orbit enough so that it'll miss us. That's what the purpose of this mission was. So the scientists found the perfect candidates. Now, these two asteroids. So Didymos is the larger one, Dimorphos orbits around it. They're about 6 million miles away from Earth. They posed no danger at all to Earth, but we were looking for a binary asteroid system where a smaller one orbits around a larger one. And then in the next few slides, I'll show you some characteristics about the distance and the size of these asteroids. But these prove the perfect opportunity to be able to test a kinetic impactor. If you took physics in high school or in college, you probably remember kinetic energy. You might also remember talking about momentum. Well, the idea is to have an object, our satellite, not with any weapons on it, but just through its motion to be able to transfer its momentum and its energy from the moving satellite to the asteroid. And hopefully it's enough to kind of push it out of the way. I'll define momentum and kinetic energy a little bit better in a few minutes. So that is the purpose of the DART mission. So here we have the satellite. We'll look at what kind of instrumentation is on it in a few minutes. The satellite itself, we'll take a look at its size, has a couple of big solar panels, but you might also notice that there's something small over here. What's becoming more popular are CubeSats, cube satellites, very small satellites. This particular one, it's called the Licha Cube. It's only about the size of a big suitcase, weighs about 30 pounds. Has instrumentation on it, it's inexpensive, it's lightweight, and we'll see that its purpose is to observe what was going on during the collision. Licha stands for, it was from the Italian Space Agency. It's the Light Italian CubeSat for imaging of asteroids. Light Italian because it has a third less calories than a regular Italian CubeSat. So if we take a look at some of the instrumentation that's on DART, remember, no explosives, but also, unlike every other probe that we send out into space, there were no scientific instruments. The purpose of the DART mission was not to collect information. It was just to see, can we move an asteroid? So this image from NASA shows a few of their technologies that they included on there. Because obviously this satellite was definitely on a one-way trip, they decided to do some testing of some next generation items, such as the ROSA, the Rollout Solar Array. There's actually a video on the DART website that shows that unlike many other satellites which have fixed solar panels and maybe they kind of unfold or swing out, this rolls up like a window shade. You know those cheap window shades, you pull them down and then you give them a little yank and then they roll back up? That's what this solar panel, actually both of these actually do. Here's the roller and you can see it unfurling and rolling. And that's really cool to try and test those. The radial line slot array is a very low cost and lightweight transmitting and receiving dish all in one. They're testing that out. And even though it wasn't the main source of propulsion, they tried a next generation ion propulsion system. They were testing that out as well. Now, here's the Licha Cube, which you can see in this image. That is the CubeSat, the Licha Cube, when it was still attached to the DART satellite. So just a small box that's separated before it actually impacted Dimorphos. Now, these two objects here, it's a high-resolution camera called Draco and SmartNav, Small Body Maneuvering Autonomous Real-Time Navigation. I would love to have a job just making up acronyms at NASA all day. That's all they do is they have these great acronyms. These two together are part of the next generation of an autonomous navigation system. That means that you don't have to have a person sitting in mission control on Earth with a little joystick saying, oh, the satellite's up a little bit too high. We need to, lower it. We need to move left and right so that we can actually hit the asteroid. It was doing it all by itself. This is the self-driving mechanism, basically. It's the same basic idea that Tesla is trying to work on. Something that can think for itself without running over people in the crosswalk. Well, at least we don't have to worry about running over people, hopefully not aliens, but we have to be able to get our satellite to our target. And I'll show you a video later as it was coming close to the asteroid, how it was actually adjusting itself, completely self-controlled. Very, very important part of the success of this mission. So here's what they plan to do. So the DART mission was going to be traveling at about 14,000 miles per hour at the point of impact. It would hit Dimorphos, and what they hoped would happen is not to destroy it, but to change its orbit. This white circle here shows the original orbit of Dimorphos around Didymos. As a matter of fact, Didymos, I think, comes from the Greek word that means twin. That's why they named it. Oh, this is the twin asteroids. They were hoping to be able to change the orbit just enough to this blue position here. They were hoping for, I think, a minimum of changing the orbital period by at least 1 minute. I think it was about a minute that was necessary so that from Earth and from other observatories, they would be able to detect a change in the orbit. That's all they were hoping for. Just because this is a great picture, the separation of the two asteroids is only about 3/4 of a mile, so they're relatively close to each other, but the Earth is over 6.5 million miles away. So think about this. We launched a satellite at a pair of asteroids to hit one small asteroid over 6 million miles away. And we did it after a period of 10 months. That's why they call it rocket science. If you're off by a little bit in your calculations, if you're rounding too much, you throw away significant zeros that my students are always doing, you're not going to hit that asteroid. You're not going to be close. And forget about it if you drop a negative sign. Your satellite's going to be going in the opposite direction. So that's quite a feat to be able to travel that far. It took about 10 months from launch on Earth to reach Dimorphos until it reached its impact. So here's another great graphic from NASA that shows the relative size of the DART spacecraft and the two asteroids. So you could see they compare it to a city bus. These are about the same size. We can see that Dimorphos is, well, even though we consider it a small asteroid, well, they've got it in between the Statue of Liberty and the Great Pyramid of Giza. Okay, so it's not that small. It's pretty big, okay? But imagine trying to hit that. That's 6.5 million miles away. Here's Didymos, quite a bit larger than, at least in terms of physical size, than the One World Trade Center. And this is the Burj Khalifa, the largest building, the tallest building in the world, okay? So, in terms of its weight, how much do each of these weigh? So the DART spacecraft itself, you figure, well, maybe I need some really super heavy satellite in order to be able to inflict some damage to push Dimorphos out of the way. It weighs a little over 1,300 pounds. Remember, a ton is about 2,000 pounds. That's about 2/3 of a ton. Not very heavy. Dimorphos itself is about 5 million tons. Remember, a million, that's 6 zeros. Didymos, larger still, 600 million tons. I put the orbital periods of each one of these. So just so we can see, people always like to know some of the characteristics of these objects. It takes about 12 hours for Dimorphos to orbit around Didymos, and it also rotates at the same period. So probably like our moon, where we always see the same face of our moon, if you were on Didymos, you would always be seeing the same face of Dimorphos. Didymos's orbital period around the sun is about 2 years, and it rotates once every couple of hours, about every 2 hours. Okay, well, that's weird. How are we going to take something that weighs less than a ton and deflect something that's 5 million tons? One more thing, just to give you a frame of reference. Less than a ton, 1,300 pounds. Well, I went and looked up for the very first economy car that I owned. It was a 1980 Datsun 210. It weighed about 1,600 pounds, a little bit more massive than the DART spacecraft. So think about this. Let's say we want to launch my Datsun into space, and at 6 million miles away, I want to hit an asteroid and move it, an asteroid that weighs 5 million tons. That's a remarkable feat. Incidentally, this is actually a photo of my Datsun. It might look like it's been defaced to you. You may be able to see here it says just married. Yeah, this damage was done by my wedding party. This is a picture from nearly 35 years ago of my Datsun. And so they went out and just spread shaving cream all over it. There's a couple of paper bells hanging from the wiper blades, but you could see from the wet ground, fortunately, it was pouring like crazy on the day we were married. So as soon as I drove out from underneath the hotel awning, all the shaving cream washed off. But we did have that lovely menthol smell inside for quite some time. So why can this work? Why can I fling my Datsun at a 5 million ton asteroid and move it? Aha, physics. All we need to do is study some science, do some calculations. Well, obviously we're going to do simple ones here. For the actual satellite itself, has to be a little bit more complicated, but the basic principles are relatively straightforward. You may have heard of Sir Isaac Newton. He had 3 laws of motion. His first law of motion said that an object will remain at rest or in motion until something pushes on it, something acts on it, whether it be friction to slow it down or a 1980 Datsun coming by and hitting it. So we're going to take advantage of Newton's law. Now, I had talked about the satellite wanting to transfer momentum. Momentum is a tendency of an object to keep moving. In physics, we use the letter P for momentum. Well, we can't use M for momentum because M, we always use it to represent mass. So the momentum of an object is its product of the mass of the object times its velocity. If something is more massive, it will have a greater momentum. If it has a greater velocity, it will have more momentum. For our introductory physics classes, we do experiments with conservation of momentum, where we'll have light objects moving quickly, smacking into a heavier object, and we can see that the velocity of each changes before and after collision. So NASA scientists had done some calculations, and they said that the DART spacecraft would have only about 1/2 of 1% of the momentum of Dimorphos, yet it would be sufficient to make a detectable change in orbit. That's great. Now, the other thing, remember what we called the DART spacecraft a kinetic impactor. We want to transfer not only momentum, but the kinetic energy of the moving satellite to the asteroid to be able to move it. So kinetic energy, the energy of a moving object. And our equation, K for kinetic energy, one half times the mass times the velocity squared. The units, we have some strange units for certain things that we do in physics. The units that we use are called joules. That's a unit of energy. A joule, 1 joule, is the amount of energy required to accelerate a 1 kilogram object. So it's acceleration at 1 meter per second squared for 1 meter. That's what 1 joule is. I brought from my lab, I hope you can see this. This is a 1 kilogram mass, weighs 2.2 pounds, just over 2 pounds. You put this in your briefcase, you think, it's only 2 pounds. Oh, it hurts your shoulder, okay? So the amount of energy that I could impart on this, if I could accelerate it at 1 meter per second squared for a distance of 1 meter, would be 1 joule. Well, let's do a simple calculation and figure out what the kinetic energy of the DART spacecraft is. Same calculation as before, always start with the equation that you're using, 1/2 mv squared. We have to use the metric system for our calculations so that it works out to be joules. The mass of DART is about 610 kilograms. 14,000 miles per hour translates to 6,100 meters per second. We have to remember we have to hit the square button on our calculator. That is 11 billion joules. So that's 11 with 9 zeros after it. That's a lot of energy. So that's what we were counting on, that the satellite, even though it was small, it could impart its momentum and its velocity from the satellite, transfer those to the asteroid to be able to move it. So took 10 months for DART to travel through space. At the actual distance that it traveled, because it doesn't go in a straight line, it was something like 400 million miles. And here are the last 5 minutes of DART's life, squished down into 40 seconds. So these images are taken from that high resolution camera that's on DART. And once I start the video going, you can see it's heading for Dimorphos. You'll see it make some corrections. That's the guidance system taking over, the autonomous system. There's no pilot on Earth with a joystick. So let's watch this. If you were fortunate enough to watch this live, that was being streamed in, you may have been sitting at home watching this saying, wow, this is amazing. We're seeing actual video of this satellite passing one large asteroid and on a collision course with a second one. And the best part about this video, I remember while I was watching it, was as it got to the end, the images kind of stopped. So I kept saying to myself, bam, 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 bam. And it just kept going. It's like, oh, until finally you can see at the bottom, it says partial image. Kept expecting each one of those to be the final image as it came in. And it kept sending back more information right till the very last second before impact. Unbelievable. Now, remember that there's that CubeSat, the Licha cube, had already separated so that it can watch what happened after the impact. This series of images shows what the Licha cube actually was able to see. So it actually was flying around on its own orbit, starts around 500 miles away just after the impact, passes by the asteroid, and then continues to about 200 miles away. And you can see all that stuff spraying out. That is material that from the impact site being ejected into space. So you could tell it was clearly a success, at least in terms of hitting Dimorphos square on. This is the view from the Licha cube. Here's another view. This is a still image that shows high resolution images of all of that ejected material. And these little squares represent something that the NASA scientists actually did to enhance the contrast, so that when you look closer and closer, you can see more structure in these ejected plumes of material. By studying these plumes and the direction that the ejected material is going, we have a better idea about what the actual composition of Dimorphos is. Now, those were the views from right next to the impact. How about from two of our largest space telescopes? We had everybody, all eyes were on this collision. On the left, this is a few still images put together as a movie from the Hubble Space Telescope, and on the right, from the brand new James Webb Space Telescope. Hubble observed at visible wavelengths, even into the ultraviolet, which explains part of the bluish color. And James Webb is an infrared telescope, which explains the reddish color. But both show that after impact, the brightness of the whole system increased quite a bit. The estimate was by at least 3 times. It got 3 times brighter after impact. So that's pretty cool. Both big space telescopes were watching this. We were also watching from the ground. There are lots of images from very large observatories that are Earth-based. This is the best sequence that I found. This is from the University of Hawaii, the Institute of Astronomy. They are operating the ATLAS, Asteroid Terrestrial Impact Last Alert System, yet another great acronym. It consists of 4 telescopes. 2 of them are in Hawaii in the northern hemisphere, and 2 of them are in the southern hemisphere, one in South Africa and one in Chile. So these images, so this is a sequence of still images put together to make an animated movie. Every 40 seconds, they took a picture, and you can see that dust cloud just coming off of the asteroid. So you can see all that material being ejected and blown off into space. That's remarkable. These are extremely large telescopes that are on the ground. So, and there were many more images, but this was the best one that I found. I love this one. So, well, we know clearly that we hit Dimorphos. Did it actually make a difference? Did we do anything? That's the whole purpose of this mission. Yes. We were hoping, I put myself in with all these NASA scientists. We're hoping for at least a change of about 1 minute in the orbit. It turns out that after impact, you can see that the orbit itself was shortened by over half an hour, 32 minutes shorter. Now, until last night, 32 minutes was the number that NASA had been talking about. And I'll talk about this in a second. Just last night, I found out they say, oh, it's now 33 minutes. They have better information now, 5 months after impact. The original estimate was 32 plus or minus 2 minutes. Now it's 33 plus or minus 1 minute. But it definitely made a huge difference in changing the orbit. So how did we know this? How do we know that we actually changed the orbital period? 2 ways that we can tell. Hello, pup. 2 ways that we can tell. One is through radar observations. Now, unfortunately, one of the best radar telescopes that we had on Earth, the Arecibo telescope, collapsed just a couple of years ago. But the Goldstone telescope, which is in Southern California, still can project radar images, can bounce off of the double asteroid system, and then get picked up by the Green Bank Observatory in West Virginia. I'll show you a picture of the Green Bank telescope at the end of my talk. Now, radar images are, every time I've heard it talk about it, I think I understand what they mean, but they're not like optical images, because radar images deal with velocity. So this sequence of images here, the circle goes a smaller dot, which represents Dimorphos. That's the asteroid that we hit. Didymos is the larger one, but it comes across as this circular arc, and it has to do with the velocity because it's moving faster than the smaller asteroid. And so radar images tend to show velocity and a distance, is it coming towards you or going away? Part of the Doppler effect. So like one side of the image means that it's approaching you, the other means that it's going away. So radar images always look weird. But from studying this, you can sort of tell that the circled object is not always in the same place with respect to the large arc. So from those measurements, they can determine that the orbit of Dimorphos was actually changed before and after impact. The other way that we can tell is by studying eclipses. We know that just over a year from now, we have a solar eclipse going to occur right in Tupper Lake, okay? Actually right through Potsdam, where I'm sitting now. But we can have 2 asteroids eclipse each other. They're orbiting around each other, and as Dimorphos, the smaller one, goes in front of Didymos, the brightness of the system decreases a little bit. So these are light curve graphs. Now, it's kind of complicated to look at all these little splotches. It's like, what are they showing? It's like, okay, these gray arrows. So first of all, September 27th, this is 1 day after impact. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days after impact. The gray arrows show for the expected orbit before we made impact of 11 hours, 55 minutes, where the dip in brightness would occur because of the eclipse. The gold arrows show where it should be, where it actually is observed now. And you can see it was getting, it was close to the original and getting farther and farther apart, okay? And that gives us our new orbit. So what these pictures on the bottom show, so for September 29th, they kind of zoomed in on all this data. Here is where the eclipse occurs. This is where it's observed now, but this is where it should have been before impact. You can see that there's a difference there. And this is time along the bottom. UTC is universal time. Instead of saying Eastern time, Western time, this is time at 0 degrees, the 0 meridian in Greenwich, England, universal time. We can see that this picture, October 4th, also shows that from the original orbit, the eclipse was expected to occur here, but now it occurs here. Here's something that's neat. Where it's observed now was before the expected early on, and now it's after. So we really have changed the orbit. And I had just read something that also said that citizen scientists, amateur astronomers, can actually use occultations of bright stars by the pair. And they're starting to collect data to also help contribute to figuring out what the actual orbit is. That's really exciting. So here's the breaking news. Now, I made the mistake last night at about 10 o'clock. I was just about ready to quit for the night. It's like, oh, I need to look up one more thing on NASA's website. And as of yesterday, March 1st, they had brand new breaking information. I was like, uh-oh, I need more slides. NASA's DART data validates kinetic impact as a planetary defense method. 4 papers, they talk about 4 papers in this article that were produced that all say, yes, the mission was a success, and this is definitely a viable way of keeping us safe if we have enough time. That's the key. Now, if we find something that's right on top of us, it's not going to work. But we'll watch a video in a few minutes that shows we're watching the skies. I'm grouping myself in again. NASA scientists, astronomers around the world are watching the skies all around, all the time, for these near Earth objects, keeping an eye on them. Now, in the caption here, you can see it now says 33 minutes. And one of the papers says that the orbit decreased by 33 minutes. The other interesting thing is we talk about this transfer of momentum between the satellite and the asteroid itself. Depending upon what kind of material it's made out of, and its composition and how tightly packed it is, the ejected material can actually also contribute to the transfer of the momentum. And it turns out from their calculations, in order to get that big a decrease, those plumes of material also created their own forces and contributed to decreasing the orbit on top of just the impact from the satellite itself. That's great. Another paper said that the impact at the moment of impact, the velocity, the speed impacted upon impact, changed the speed, decreased it by 2.7 millimeters per second. Millimeters. There are 10 millimeters in a centimeter, and there's 2.5 centimeters in an inch. A really, really small amount. But as time goes by and scientists have more time to analyze the data that they're collecting, they can get more and more information out of it. A couple of the other papers that they talk about in this article had some great pictures. So this is a picture from DART that was taken about 3 seconds before impact. So some other scientists have figured out that this is exactly where it hit. Here's the DART spacecraft. Here is its big solar panels. In between, right smack in between these 2 large boulders, and according to their measurements, the the largest boulder, this one over here, is about 21 feet across. It's pretty big, but they figure it hit exactly there. And with computer modeling, here are those 2 boulders again that hit in between. The white line represents the satellite's trajectory in. So this represents if you were hanging out on Dimorphos watching, this is what you would have seen when it crashed into the surface right in there. So this terrain model came from information from DART. So fascinating stuff. And we're just going to know much more about it as time goes on. Now, one more 2-minute video from NASA that I want to show you. They also had on this news article, NASA changes the orbit of the asteroid. This one has some spoken word, and it just talks briefly about the history of the mission and their success. So let's watch this. Click. There we go.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
Wow, that makes me want to sign up with them. So it's always great when a mission is successful like that. Now, we are not done with this double asteroid system. The European Space Agency has their own mission planned. They're planning to launch in October of 2024. It's called the Hera mission. They are going back to Didymos and Dimorphos to study those asteroids, to study the impact area, and to try to learn more about the asteroids themselves. The more we know about composition and how much energy it takes to be actually to deflect an asteroid, the better off we'll be if we really need to do this in the future. You can see from their graphic here, they've even got a big divot worked out in Dimorphos. So here's just a picture from the European Space Agency. They're planning to launch the mission in October of 2024. This one's going to take over 2 years to get to Didymos and Dimorphos. Now you say, wait a minute, it's over 2 years. How come it took DART only 10 months? Remember, everything is moving around, so they're in different orbits, different relative positions. Plus, they have different end objectives. You can't just send a satellite straight at an asteroid and then, Mr. Sulu, let's put it into an orbit. It doesn't work that way. So it's probably going to take a much longer path. So it's going to take 2 years to get to the system. So in December, so they tentatively have it scheduled December 28th of 2026. It's actually going to arrive at the asteroid. Now, this one will spend 6 months orbiting around the pair. You can see it has 2 CubeSats, not just one, and it also has a whole bunch of scientific instrumentation so they can get detailed studies of the crater and the asteroids themselves and what happened underneath the crater. So they're going to do extensive studies for 6 months, and one of the CubeSats is actually going to land on Didymos. So in 2027, that's probably when I'll give a talk about the Hera mission. So something to stay tuned for. So now that you have successfully sat through my talk, hopefully you haven't fallen asleep, you can pass a quiz. I'm not going to give you the quiz, but if you go to the DART website, and Seth hopefully will copy this address into the chat window, you can take a quiz and get a certificate that shows that you were a planetary defender. And if you successfully watch this, and this talk will be on YouTube, so you can go back and review. If you pass the quiz, 10 questions, multiple choice, you can get a certificate. So I took a picture of a screenshot of one of the questions that's asked of you. This happened to be question 8 of 10. DART will be traveling at 14,000 miles per hour. How will it be able to accurately hit the asteroid? It's obviously not a rigorous test, because notice the first choice is the power of positive thinking, and the third is by using the force. Luke, you will move the satellite so that it hits the asteroid. So if you successfully complete all 10 questions, you get a certificate that will have your name printed on there. You can print it out, mount it on the wall, that says that you have been declared a planetary defender on NASA's double asteroid redirection test. Definitely worth it. So I'm going to end with 2 pictures that I want to show you. One is myself and my colleague, Aline O'Donoghue, who unfortunately couldn't come tonight, with the 3 students that we brought with us to the Green Bank Observatory this past June for our annual workshop that we have there. The Green Bank telescope, remember, this is the one that received the radar image from the Goldstone telescope. That's in the background here. That is 1 mile from us. It's about the height of the Statue of Liberty, and it's about 300, the dish itself is about 300 feet across. And we all not only got to go up here, we all got to stand way up here on top of this and look down on the dish. It's quite an amazing instrument. As my final image to show you, Seth had mentioned that we have put a concrete pad in around the observatory. So here's a nice image of it. And hopefully we get a chance to actually have some observing. Of course, as soon as we put this in, then the skies get cloudy all the time. But hopefully the weather improves on Friday nights in the future, and we'll all be able to get together for some observing. So thank you very much for your patience and for attending, and I'll be happy to answer any questions that you might have. And I'll stop sharing now.
Excellent, Jeff. Thank you so much. And
Thank
before
you.
we get to questions, let me just note that quiz I just posted on the chat, and our YouTube channel also, where this talk will be posted within the next few days. So we'll send out a notification, email, and via social media of that in the coming days. So and finally, before we talk questions, if you're interested in becoming more part of what we do, or making a donation to our observatory and planetarium construction, more specifically the planetarium itself, there's a link where you can do that. So with that, let's open the floor for questions. I know some of you had some difficulty staying on Zoom. I think this, whatever version we've upgraded to, seems a little bit buggy to me. I know some of you got kicked off and had to join back in, but I appreciate everyone's patience while Zoom fixes the issue, whatever that is. What questions do we have for Jeff? I know something
I have a
that,
question.
oh, yep, please go ahead.
Oh, hi. Thanks for the talk. It was great. I really appreciate it.
Thank you.
There used to be this old project Orion to power rockets by blowing up atomic bombs. They were going to build a rocket, build a massive shield behind it, and blow off atomic bombs underneath the shield.
I remember hearing about that.
Yeah. I just wondered if they ever thought of doing that, like not a bomb to blow up, the asteroid, but to push it, like in the
Push,
Orion
yeah.
project.
Right. And I know that this is just one of several ideas they have to deflect asteroids. There are ideas of, well, if it was large enough, that an impactor wouldn't work, could you like strap some rockets to it, gigantic engines, well, I think I saw that movie too. But that's a good idea. And I don't know what other things they have planned. I suppose as time goes on and NASA says, oh, guess what? We got a new mission and we're going to be kind of, pushing things out of the way with some sort of projectile, whether it be an engine or multiple explosions. But, in theory, that should work too. One of the things that's interesting, and this is why we need to study the composition of these asteroids, is if you recall, when the OSIRIS-REx lander hit the Bennu satellite a couple years ago, it turned out to be basically just a big pile of rubble. And so that's one of the things that they're going to be studying currently, and also once the Hera mission goes. What is the composition of these asteroids? If they're solid bodies, you're going to get a different kind of impact, and you can give a different push to it than if it's just basically a big pile of gravel that's being held together. So those kind of issues are very, very important and, kind of hard to keep track of. So we'll see what kind of ideas they come up with in the future.
Jeff, I don't know if anybody else had this, not concern, but thought while you were talking about changing the orbit. The asteroids are on orbit around around the solar system themselves. Is there a thought that perhaps in changing the orbit of one of those might cause a chain reaction for it to bump into something else and bump into something else that may actually land in Tupper Lake?
So you're playing a lot of pool, right?
Yes, exactly.
You just want to sink one ball, but they all go in. Yeah. And the thing is too, despite the animations that show it very densely populated, there's a lot of space out there. Okay. But yeah, that's obviously something we have to consider, is if we change the orbit of an asteroid, we want to make sure that it's not going to impact something else and then cause other problems, for future generations to worry about where it would land in Tupper Lake. So presumably, this is what all the rocket scientists have to figure out, is not only if you change that orbit. And again, that's why they chose this pair of asteroids that were sufficiently far from Earth that posed no danger to Earth directly or presumably indirectly. There was nothing else close by. And by changing the orbit of Dimorphos a little bit, it's unlikely that it's going to crash into Didymos and then cause that to go somewhere else. So yeah, these are all the calculations that they have to run through their supercomputers and project into the future. Well, where is it going to go if we hit it here or here or here? So
that I can't remember the acronym of that additional little camera that was floating out there taking pictures.
The Licha cube.
The Licha cube. Is that still imaging? Are we going to get more images from that?
That's a good question. I haven't heard anything else about it.
Is there still film in the camera?
Yeah, I would certainly hope so. I would have to look that up, because everything else concentrated on the DART, satellite itself and the impact. And, we saw those sequence of images from the Licha cube. I haven't heard anything else. So that's a good idea. That's a good question. I'll have to look that up tonight while I'm drinking my glass of wine.
Well-deserved glass of wine.
Well-deserved, yeah.
How about more?
I find it interesting that we think of a moon orbiting a planet, like the Earth or Jupiter or Mars, but here we have an asteroid being circled by another asteroid, sort of like a little asteroid moon. It'd be interesting to consider that.
Right. And we have, stars that orbit other stars. And, you know, it turns out that our sun is in the minority in being a single star. The majority of stars that we see are in multiple star systems, even if we can't see them with our eyes. There's a lot of them out there. So yeah, there's a lot of things. Once you get objects that have large gravitational forces, they interact with each other. They start orbiting around. Galaxies interact with other galaxies, just on a much longer, more distant and a longer time scale. So yeah, it is interesting. You keep going smaller and smaller, you still get these little solar systems, so to speak, that keep forming. So
Everyone likes company.
yeah, exactly.
All right. Well, with that, I want to thank you, Jeff, for your expertise and information tonight. It's always a pleasure hearing you talk about these things with such enthusiasm, even if it is a little bit scary. And and thanks to everybody out there for joining us. If you had difficulty, please let us know what in staying connected tonight. If you think that it was something related to us, I'd want to know that. I don't think it was. It may be just a lot of internet traffic tonight, or I know there's a lot of solar activity these days, so that may actually be part of it. Who knows? But I would want to know that just to make sure we're providing the best user experience when flying with us, the Adirondack Sky Center and Observatory. So with that, I will see you back here next month with Eileen O'Donoghue, and I hope clear skies for everybody. Good night.
Thanks, Seth. Thanks, Jeff.
Thanks a lot. Thanks for coming, everybody.
Very interesting.